Okay, everyone, we're going to get started. So welcome to this lecture. This is the second lecture in our course, AI in the Sciences and Engineering. In this lecture, I'm going to be covering an introduction to deep learning. And so this is the first part of 2 lectures on this subject. So before I do that, let's just recap what I covered in the last lecture. In the last lecture, I gave you a very high-level motivation of the course and introduction to the course. And what I hopefully tried to show you was that AI is really having a massive impact in science and is driving a lot of breakthroughs today. So I talked about examples from using AI to carry out really fast and accurate climate simulations and weather predictions. I also showed you an example of using AI to help control fusion in nuclear reactors. And AI can also help us predict much more fast the 3D structure of proteins. I also talked about the kind of key scientific tasks that we often want to solve when we're doing scientific research. And I also tried to motivate the ways that AI could help us solve those. So for example, helping us solve simulation tasks, maybe making them more efficient or faster to run. Helping us solve inverse problems, understanding underlying parameters from observations of a system. Perhaps AI can help us more accurately determine those parameters. And then I also talked about equation discovery, and instead of relying on human intuition, can we have an AI learn kind of to discover unknown physics, for example? Okay, and then I also try to introduce this field, which is called scientific machine learning, and this is kind of the state of the art of using AI in scientific research today. And this field exists because we realize there are many disadvantages of using machine learning, or maybe flaws of machine learning. For example, lack of interpretability, the amount of training data that we require. And so what we try and do in this field is really tightly blend our existing scientific understanding with ML to make models that are more powerful, more robust, more interpretable. Okay, so here's the course timeline that I showed last lecture. So we're on the second lecture, like I said, the first lecture of 2 on an introduction to deep learning. So what we're going to cover in this lecture, it's a fairly high-level coverage of deep learning. And so first I'm going to explain what deep learning is. And I'm going to explain multi-layer perceptrons, one of the most basic neural network architectures there is. I'm also going to talk about the universal approximation of deep neural networks. Then I'll talk about the popular tasks that we use deep learning for, so things like supervised learning, unsupervised learning. These are kind of classic machine learning tasks that we want to solve. And then last, I'll talk about how we train deep neural networks, and in particular, gradient descent and backpropagation. Okay. So yeah, by the end of the lecture, hopefully you'll be able to mathematically define what a deep neural network is. You'll be able to understand the typical types of tasks that we use neural networks for, and explain how they're trained as well. And then by the end of these 2 lectures, I should have covered enough material that you'd be able to explain at a bit lower level how ChatGPT, this super popular model, or more generally how large language models that are trained, and also the architecture that they use. And you should be able to understand how these work. Okay. So just to start off at a really high level, and this is a slide that I showed again in the course introduction. AI research has really exploded in the last decade or more. And I showed examples of AI impacting the world today, and I just talked about ChatGPT. We have now large language models that can have conversations with us and do really remarkable things. We also have AIs that can generate really realistic images and videos now. We have AIs that can do multitask, can solve multiple tasks at the same time. So, for example, Gato is able to classify images and have a conversation with you and play games. And AI underpins a lot of the technologies that we use today. So, for example, speech translation or text language translation, also helps us code GitHub Copilot, for example. And the technology that is really driving AI research and has driven AI research, or I would say 99%, or maybe 90%, is deep learning. And so why is deep learning so popular? Well, again, this is the slide that I showed in the introduction. There are broadly three main reasons. The first is there is a lot more data in the world today that we can train these algorithms on. Hardware improvement has improved, so we can train much bigger models. And also, there's a lot more software out there today that makes it really easy to train neural networks. So we have PyTorch, TensorFlow, and also a lot more architectures and a lot more innovation in the theory behind these models as well. Okay, so before I explain deep learning specifically, I want to just put it in the context of the broader field of AI. So AI, machine learning, deep learning, these are terms that are used fairly vaguely today, or are kind of hard to define sometimes, or people have different definitions of them. But what I'm going to say is, or what's important to realize is that machine learning and deep learning is one specific part of AI. And for the purpose of this course, I would define AI as, training an intelligent agent to be able to mimic human behavior. And learning about the world, kind of learning about the rules of the world, is just one aspect of what I would expect an AI system to be able to do. You can imagine, like, once you've learned some rules, you don't just want to know those rules, you want to be able to do something about it. So, for example, if you've learned a lot of mathematical logic statements about the world, you might want to infer things from those statements. Or if you've learned about transport systems, you might want to be able to then plan a route from A to B. So learning is just one part of an autonomous system. So machine learning is concerned about learning the rules of the world, and then deep learning itself is just a specific part of machine learning, which is using specifically deep neural networks to learn patterns or learn these rules. So yeah, we're going to focus a lot on deep learning, but it's really important to appreciate this wider field. And if you're interested in getting into AI more generally, there's a lot of really great material out there. The one that I would recommend is this book, A Modern Approach from Russell and Norvig. This is a kind of classic textbook which gives you a wider introduction to AI. Okay, so if there's one thing that I want you to take away from this lecture, is this idea, and it's the idea that neural networks are very simply just flexible functions that are fit to data. So that's quite a simplistic view of neural networks, and of course there's a whole variety in many different architectures and a lot of complexity when training networks. But this is really useful, especially when we're going to apply neural networks to scientific problems. This is a very useful way of thinking of them. So what do I mean by that? So it's very simply the neural network takes some input, and this input is usually a vector, x. It passes it through some mathematical function. The neural network architecture itself defines that function. And that architecture has some free parameters theta that we're going to tune. And then the network produces an output y, which again is another vector. And what the training process of the network is to try and match those outputs of the network to some training data by tuning the values of theta. So an example, a very simple example, would just be, given this data here, so this is noisy measurements of some data sampled from just a polynomial, for example. Given those y values, can we produce a function that fits that curve, basically? So it's simple curve fitting. And so, that's exactly it. Neural networks are simply flexible functions that are fit to data. Okay, so I hope that most of you know about function fitting already and have done function fitting before. And kind of, if we just assume that this data here is just from a polynomial, then the classic way of doing it is just to do polynomial regression or actually just linear regression. This is something that hopefully everyone has seen before. So how would we do it if we were just going to do linear regression? How would we do function fitting? So first, we would just assume a model of the data. So we would say, OK, I'm going to assume that these data points follow a polynomial curve. So y hat is our approximation of the true function. And the only thing is we don't know what the coefficients of the polynomial are. So these theta 1, theta 2, theta 3, theta 4. So one way to frame this is to say I'm going to use least squares to estimate what theta are. So I'm going to choose a theta star, my best guess of what theta is, by minimizing the least squared difference between what my model predicts and my noisy training measurements. OK, so this is just least squares regression. And we can just rewrite this using linear algebra. So we can say that all of the outputs, all the predictions of my model, these y hats, for each training data point, just equals this matrix, which is our values of x and their powers, times by our vector of, or our column vector of thetas. And then we can rewrite our least squares objective as minimizing theta in this matrix equation. And you can show for this polynomial or linear regression case, there's an analytical solution, so you can compute this analytically, and it just involves computing an inverse of this phi matrix. OK, great. So hopefully that's something you should be very familiar with. So how is neural network regression different? Well, to be honest, it's very, very similar. It's exactly the same idea where we have, again, some function, some neural network function, which we're going to try and fit to this data. Typically, a very popular method, again, is to use least squares. And we're going to use exactly the same objective, where we're going to say the outputs of the neural network, or the difference between the outputs of the neural network and my training data should be minimized. And we'll choose a theta value that minimizes that. So really, the only difference here is that, in general, I haven't told you what that neural network function is. And if we don't know what that function is, in general, we don't have an analytical solution. And so we have to resort to some other way of learning those parameters of the network. And so 99% of the time, we use gradient descent to train deep neural networks. And so that involves taking the derivative of this loss function with respect to the weights of the network, and then doing a gradient descent step with some learning rate. So yeah, that's it. That's a very simple description of how we train neural networks, and this is the case for nearly every neural network that we train. So the next question really is, OK, so what exactly is that function that we're defining, neural network of x? And as I said, this just depends on the specific neural network architecture that you choose. And the one that I'm going to cover in detail is this multi-layer perceptron. So this is probably one of the most basic architectures that has been around for the longest for a neural network. MLPs can be defined with a varying number of layers, but for a two-layer MLP, the actual equation for it is given below here. And so we take our input x, we times it by some weight matrix, we add a bias vector, pass it through an activation function, this is a sigma value, and then do the same process again depending on how many layers we have of the network. And yeah, that's the simple mathematical definition of an MLP. So you have to ask the question, like, why do we choose that particular function? Like, there are so many different functions we could choose with free parameters in. Like, why does everyone use this particular function? It seems a bit arbitrary. Well, I mean, the reason why we use neural networks and these functions is because neural networks are inspired by biology. I mean, this is the reason why this field started, is because we wanted to train algorithms that were more like how the brain works. And so there's a caveat there that neural networks definitely a very simple approximation of the brain, and what the brain does is much, much more complicated than this, but it's a good analogy at least. And so if I took just a single output neuron of the MLP here for the last layer, and I just draw the how it processes its inputs and gives you its output, you can see that it takes the activations from the previous neurons. times it by these scalar weights, sums it together, adds the bias, and passes it through an activation. And this is indeed kind of a simple view of how a biological neuron would work. So, this is a diagram of a neuron. It has some inputs here that are being activated. It processes those inputs and produces a spike depending on their values, and then passes it to neurons further downstream. So this is kind of similar to what a neuron is doing in a neural network. And so then if I this is just for a single neuron in the last layer. If I write an expression for both the neurons in the last layer, I can actually just turn that into a matrix equation, where I put my weights inside this matrix here, times them by all the activations from the previous layer, and add this bias vector. And then you can see how we can arrive at this equation that I explained before that defines the neural network function itself. And so to add more layers, we just compose each of these layers together, and we can just say that the neural network function is just a composition of these layer functions, these G and F functions. Then the final thing I haven't really talked about is the actual activation function itself. And so there are many different choices that you can make of the activation function. Probably the most popular one that is used is the ReLU activation function, which is just 0 when the summation here is less than 0, and otherwise the value of the summation if it's greater than 0. We're going to be covering a few different activation functions in the course. One that we use a fair amount for scientific work is tanh, or more generally continuous or smoothly varying activation functions. So, for example, in physics-informed neural networks, these are very useful, and we'll explain why in that lecture. So, yeah, I've given you all the tools necessary to be able to train the neural network, define it, and train it. And so this is just an example of a MLP given by this function here, fitting to this training data that I've been showing you. And you can see as it trains, it starts off at a very kind of smooth function that doesn't vary much and slowly fits to the data. And so this is an animation of the function estimated by the network as the function of training step. And I just think it's really interesting to see how these things evolve and train. Sometimes it's kind of hard to understand exactly why it trains in a certain way. One really interesting thing you can do is plot the weights of each, the weights for each neuron and how they evolve over training step or over time. So this little animation on the right, the width of the line is just proportional to the absolute value of the weight. So what's kind of interesting, as you can see, even though this is a very simple function, the output is a summation over a distribution, is distributed over the hidden neurons. So it's not like a single neuron is just producing the output. And so this actually is the reason why neural networks are actually sometimes very hard to interpret, because of this kind of distributed representation that they learn. Okay, so it does kind of beg the question, like if I'm doing like simple curve fitting, a polynomial curve fitting, why wouldn't I just use linear regression? So can anyone give me an answer why it's a good idea to use a neural network for function fitting? Yeah, go on. Yeah, definitely. So the clue is in the title. So it's this property of neural networks called universal approximation. So what does that mean? So neural networks are just simply flexible functions that fit to data. But what's special about them, and what's different to, say, like polynomial or linear regression, is that with enough parameters, and I'm saying this in a very imprecise way, but this can be much more formalized, using mathematical theory. With enough parameters, neural networks can approximate any arbitrarily complex function. And this is the universal approximation property of networks. So this is really, really, really great, and what makes deep learning so powerful, and what makes deep learning applicable to all these different tasks that it's been applied to, today. So I can learn not just simple function fitting, but I can learn really complicated functions. For example, the function that takes an image to like a classification of what that image is. This can still be thought of as an image. How is an image this can still be thought of as a function. So how can an image be thought of as a vector? Well, it's quite easy. You could just imagine each value of the pixel in the image is just an element of the vector. And the classification is we just interpret the output of the network as a class. And so, yeah, this is a really, really great property of neural networks, and this is what makes them so powerful, is that we can train them to do many, many different types of tasks, which probably a linear model wouldn't be able to do. And so what makes it nonlinear, rather than just a linear function? Well, it's the activation functions. You can see if we just went back to this definition of a neural network here, what happens if I just took out the activation function? So I didn't pass it through any activation function. What would happen? Anyone tell me? Yep.
It would remain a linear function.
Yeah. So a matrix times by matrix is another matrix. You just collapse it into one linear function. And so if you do like a classification without activation functions, for example, you just fit like a linear classification to this data. So it really is these activation functions that allow you to draw these kind of nonlinear relationships between your data. Okay, so we talked about MLPs, so I'm going to try and explain to you a different type of architecture now, which is the convolutional neural network. And I explain why it's useful to use different architectures than just a standard MLP. So we're going to take this example again of classifying an image. And we're just going to think about, if we used an MLP, just the number of parameters that we would need to do a simple classification task. So as I said before, we could think of the input image here as just a vector where we flatten out the image, and each pixel value is an element of that vector. But that already is a really massive vector. Like if we have the image as 128 by 128, so a very small image, then you remember that each layer in the MLP is fully connected, so each neuron is fully connected to all of the previous neurons. Then you can work out the size of the first weight matrix is going to have to be, assuming there's 100 neurons in the first layer. It would be 100 times by 128 times 128. So this is already 1.6 million parameters just in the first layer of the network. So that's a huge amount of layers to do a fairly simple classification task. So it doesn't really feel like an MLP is the right architecture to use, and is very likely to overfit to this data given the amount of parameters it has. So how is a convolutional neural network different? Well, it's used for the same task, so we're still going to classify the image, but the way that the neurons see the input is different. And so, again, we have a hidden layer of the first hidden layer of neurons here, and we lay them out so that they have the same shape as the image. And the important difference is that each neuron in that hidden layer only sees a few neighboring values in the input image. So, for example, it sees like a 3 by 3 or a 2 by 2 patch of the image. And so then this neuron here is not connected to the entire image, and so therefore has many less weights that we're multiplying the image with to get that activation of that neuron. The other really important difference of convolutional networks is that each neuron here shares the same weight values, so they all apply the kind of same filter to their patch that they see in the image. So this dramatically reduces the number of weights inside each layer of the convolutional network. In fact, for example, if each neuron just saw a 3 by 3 patch of the image, then you would just have 3 times 3 weight, 3 times 3, which is 9 weights in the network. So that's dramatically different to, 1 point however many million weights in the MLP. So mathematically, we can just write this as a cross correlation, and this is the expression, and it looks similar to how a fully connected network would look. It's just that we're doing a summation over this filter. And CNNs are a really good choice for other reasons too. They have a lot of interesting properties, and the one that is most known is their translational equivariance. And so this is the idea that the head of the dog, for example, would give you the same activation no matter where the head is placed. So there's translational equivariance to the input image. That sounds strange. Is it the radiators or is it the blinds? Or hard to say. Okay, I'll try and carry on anyway. So in practice, we usually extend CNNs to have multiple input channels and multiple output channels. So for example, the image of the dog usually has like a red, green, and blue channel to it. And so we can do the same with each layer of the convolutional network as well. It can have multiple channels. And then what we say is each neuron in each channel is not only connected to a single channel in its input, but also all the other channels too. So you just build out the weight matrix and sum over the channel dimension as well. And so that's the extra summation that we're adding here in our layer function. So this gives us a few more weights, but makes the network more expressive, and it can learn features across different input channels. You can also extend CNNs to their 1D, 3D, or even ND equivalents as well. You can see how that would follow analogously. And yeah, there's a lot of innovation on other tricks for CNNs, like, for example, adding dilations, not having neural networks connected to every single neighbor, but maybe every other neighbor. And strides similarly. So one really interesting thing that was realized quite early when we're training CNNs is that actually the depth really matters. So a good question is, how big does the neural network need to be? How many parameters do we need to have to be able to train the network? To be able to perform well and be able to classify images well. Well, it actually turns out that a really important thing to do is to train a deeper neural network and not just a wider neural network. So not just to have more and more channels or more hidden neurons, but to have more and more composed functions. And what you can do is like query each kind of layer of the convolutional network to see what it responds to in its patch. And what we can see is that the first layers of the convolutional network respond to kind of very simple features, for example, edges and curves in the input image. But then as you get deeper and deeper down into the network, you can see it starts to be sensitive to more and more complex features. So, going from maybe things that look like ears and noses to entire faces. And so CNNs or neural networks are really powerful at learning these like complicated features. So you can do this more numerically and plot the performance or the test accuracy of different neural network designs. So, for example, like a fully connected network with just three layers, or a convolutional network with 3 layers or 11 layers, and you really see that it's the depth that matters in the accuracy of the network, and not just the number of parameters that the network has. So what does this mean? What we're really doing in a very general sense is encoding into the network function like a prior or an inductive bias, we call it. And this inductive bias is that the true function that we're trying to model is a composition of simpler functions. And this is kind of a powerful idea in what is the type of inductive bias that we're encoding into our neural network architecture. Okay, so I've given you a brief overview or recap of what neural networks are and how we train them. So now I'm going to go through some of the popular deep learning tasks that we often train neural networks on. So in particular, I'm going to talk about supervised learning, and I'm going to cover regression and classification. Then I'm going to talk about unsupervised learning and feature learning, autoregression, and generative models. But I think I want to go back to this point that I said at the start. In all of these cases, even though we have maybe a different objective and a different way that we use our training data, in all cases, the neural network is still a function that is fit to some data objective. So supervised learning. So this is where we have typically we have some inputs and we have some labels or outputs of the function that we want to model. In regression, it's a continuous function that we want to model. And as I said before, the setting here is we have a set of inputs and outputs, example inputs and outputs from some true function or maybe some noisy observations of that true function. And then we're going to use a mean squared error as our loss function or our objective function to minimize, to estimate the weights of the network. Okay. So what's very useful is to frame this as from a probabilistic perspective as well. And this can really help us interpret how the network is learning and also deal with this kind of in the situation where we have some noisy data rather than exact measurements of the function, for example. So how would you frame this from a probabilistic perspective? So you would say, well, instead of trying to fit a function, what we actually have some y value, some conditional distribution. So these y values are sampled from this distribution given the values of x. And we actually want to approximate the conditional distribution itself, and we're going to say there's some values of theta here that we want to find that best approximates this distribution. So how would we train the network from a probabilistic perspective? So often we have to make some assumptions, and like a common one in this setting is to just assume that this conditional distribution is just a normal distribution, where the mean of that normal distribution is the output of the neural network given the value of x, and then maybe the standard deviation is just a single number, or we could try to learn that as well sometimes. Then we have to make a couple more assumptions. We say that the training data, or each training data point here, is independently and identically sampled from the same distribution, so from the same normal distribution. And that allows us to write the probability of our entire data set, so the probability that we observe x1, y1, x2, y2, etc., given our values of theta, and we can write it out with this product. And then we just use a very simple technique in statistics, which is maximum likelihood estimation. And that's just to say that we're going to guess that our best values of theta here are the values which maximize the probability of the data given the value of theta. So how do we maximize this expression here? Well, given that this is a normal distribution, we can just put in a normal distribution here, and then you can see quite quickly that the maximization of theta here is the minimization of this expression here, which is the same as the loss function we used before. So it's a really nice way to interpret loss functions from a probabilistic perspective, and depending what distribution you choose, changes the loss function that we'll use to train the network. Okay, so let's move on to classification. So how is classification different to regression? Well, from a probabilistic perspective, we're still trying to estimate a conditional distribution, which is, given the value of x, what's the value of y? But from a classification perspective, this distribution is now a discrete probability distribution rather than a continuous distribution. So we assume that y is a sample from some finite class of possible values of y. So for example, in this very simple image classification task, we can say y is either a dog or it's a cat. So there's only two possible classes that it could be. So how do we define an appropriate loss function in this case if we want to train this network? So one way to do it is just to say each class is going to be encoded as a one-hot vector. What does that mean? It just means that if the output is a dog, then we're just going to say y is this vector 0, 1, and if it's a cat, then it's the 1, 0 vector instead. And then we have to assume some form of this conditional distribution. So we'll say now it's just the output of the network itself is just going to represent the probability of that class, given by this expression here. And you can see how that would the probability is just because this is a one-hot vector, it just pulls out the probability. For example, if this neuron, if this neuron here tells us the probability of the dog, then this product here is just going to pull out that probability because it's a one-hot vector. And we have to make sure that to make sure our probabilities are all correct is that the summation over the outputs of the network should equal 1, so that we have a well-defined distribution. Okay, and then we do exactly the same workflow, so we use maximum likelihood estimation again. We assume that each of our training data points is identically and independently distributed, and then we can write out our probability of our data in this way again. And then it's the same idea. So we maximize the probability of the data given the value of theta, and we end up eventually with the minimization of this expression. And this is known as cross entropy. And yeah, that's the standard loss function for training classifiers. Okay, so one other thing I said before, we had to make sure the outputs sum to 1. And so the typical way that we do this is we use a softmax output layer of the network to ensure that. And so we just say the final activation here is normalized by the summation over the outputs, and that makes sure that it sums to 1. Okay, so let's move on to unsupervised learning tasks. And so again, remember I said neural networks are functions fit to data, and it's the same thing here. It's just the data that we're fitting the network to is slightly different. So we don't have like explicit labels and explicit inputs. We just have some data set, and we're going to try and learn some function that learns something like in the middle of that data set somehow. So for example, feature learning is one unsupervised technique. And it's the idea that we can take an image and we can say, well, actually, that image can be compressed into a lower dimensional space that contains, each element of that space is like a salient feature of that image. So maybe we could describe images of dogs by like the color of their fur and the size of their head, for example, and they're like two salient features that we could learn to describe images with. So in this setting, we have a neural network which will compress the image down into just a vector which is much smaller than the input vector, and then decompress it back outwards again. And we have a loss function which just matches the output of the network to the input of the network, so to reconstruct the image. And just by doing this, we can force the network to learn like a salient representation, which is very useful for further downstream tasks. So for example, if we want to do some sort of clustering of the images or some extra task on top. So a good example of this are variational autoencoders. So this frames it in a fully probabilistic framework. And it's really good at discovering these kind of latent variables. So for example, if we train a VAE on MNIST, which is just lots of images of digits, and we just use two salient, we use a vector here with just two elements in the middle latent vector. And we then sample those values across their ranges and see what the output of the VAE gives us. We can see that they learn to smoothly interpolate between different numbers in the data set. Okay, so kind of related to that feature learning, like reconstruction of the data, is autoregression. This can be thought of as an unsupervised learning task. So instead of just reconstructing the whole data, the goal here is to predict forwards what will happen in the data. So it's a prediction task. So there are many different examples of autoregression. One is, for example, predicting stock prices. If you're given the previous price from the last 10 days, can you predict tomorrow's price? Or another example of these large language models like ChatGPT, where they're given a sentence or part of a sentence, and then the goal is to complete the next word in the sentence. So the task is, given many example sequences, train a model to predict the future values from the past values. So this is how one neural network architecture might work. This is a recurrent neural network. So you can imagine we have our previous values, x0, x1, x2, x3. We pass them into the network, and they're processed by some network module, and I'm not going to be specific about what that is. But it could be, for example, convolutional networks or MLPs or something like that. And then we run these networks recurrently through time, and then produce outputs after that and to predict the next values. Okay, then the final kind of class of unsupervised learning algorithms that I'm going to talk about are generative models. And so again, this is another type of task given some training data. So given many examples of X's here, so some training data set, what I now want to do is learn a distribution, or more specifically, I want to be able to sample from the distribution that those examples came from. So an example would be if we have lots of images, I want to be able to sample a new image from that distribution that's never perhaps been seen before. And so, yeah, image generation is one example. And one way you might do this is you might have something called a generative network, which, for example, might take like a random vector as a seed as the input. And given that random vector, it will process it into an image. There are many types of generative networks out there and ways to train generative models. And one of the most famous ones are called generative adversarial networks. And these generative networks look like this kind of architecture, but the way that they're trained, they also have a discriminator which helps to train the generative network by telling you or guessing whether that image has been generated or whether it's a true image. So yeah, I've given just a very brief and quick overview of the different types of tasks that we train neural networks to solve, and there are many tasks like this in scientific research that we want to solve, and so it's very useful to understand all these different techniques. Okay, in the last couple of minutes, I'm going to talk a little bit more about training deep neural networks, and in particular, how we use gradient descent to train the networks in more detail. So yeah, I already said this before. Again, most tasks that we're using neural networks for, we're trying to fit a function to data, and we use some sort of loss function. Sometimes it's least squared, sometimes it's something else. And in general, there's no analytical solution that will let us minimize that loss function. And so we often use gradient descent, and this is the kind of algorithm of choice for most training tasks. So the question is, how do we actually computationally compute the derivative of the loss function with respect to theta? And that's kind of an interesting question that's worth exploring. So what we do is we utilize the chain rule, basically, to be able to evaluate this gradient. And so, given this least squared loss function, we can already apply the chain rule once to show very easily that dl by d theta is just 2 times the network output minus the true value times by the derivative of the network with respect to theta. Okay, so we've applied the chain rule once to evaluate the gradient. So now we have to bring in the actual neural network function itself. So let's just assume that it's a fully connected network here that's composed of these layer functions. Very simple weight matrices times by the input plus the bias. So the next question is, how do we calculate what is the derivative of the network with respect to, say, one of the theta values, so the W1? So how would you go about, or how can we derive that? Does anyone know? How would someone go about finding the derivative of this function with respect to W1? Yep, go on. Chain rule, yeah. Well, what makes it a little bit harder than just a simple chain rule? I mean, that is the answer, but yeah. Yeah, so this is a multivariate problem because this function, the output of this function is in general a vector, and the input is also a vector, and we've got matrices multiplications. So what we have to do is do, multivariate chain rule. And to do that, we can evaluate this, dm by dw1. But this object here is not a scalar gradient. It's actually a matrix, a Jacobian, to be more precise, which is a matrix which contains the derivative of each component of the output with respect to each component of the weight matrix. So this is, depending on how big W1 is and the output of the network, this can actually be a really massive matrix with a lot of values in it. For example, if this weight matrix has 1 million values in, this is going to have like 1 million rows, I guess. Sorry, 1 million columns, looking at the definition. So yeah, we have to apply the multivariate chain rule. So I can actually write this down analytically, and I don't have the time to explain this in the lecture, but you can go away and write this down and prove it for yourself. If I use the multivariate chain rule, then this is the expression for the gradient with respect to W1. And it just involves derivatives of my activation function and the weight matrices and the values of X and the intermediate activations of each layer. So then we can just finally compute dL by dW1 so that L is a summation over all the examples. So we have this summation in the final gradient. And it's this expression here. And so the way that modern frameworks for doing deep learning, like PyTorch and TensorFlow, work is they use this algorithm called backpropagation to evaluate these gradients of the loss function with respect to the trainable parameters of the network. And backpropagation it evaluates exactly this expression. And for efficiency reasons, and we're going to get much more into detail in this in the second half of the course when we talk about differentiable physics and auto-differentiation in much more detail. For efficiency reasons, it evaluates this expression from left to right. This means that we can do vector Jacobian products instead of big matrix multiplies, which are very impossible to compute. So yeah, we evaluate this from left to right. And so how these algorithms work, auto-differentiation works, is that we do a forward pass first, where we evaluate the output of the network and store all the intermediate activations. And then we do a backwards pass where we compute the gradient from those values. Yeah, and I've just shown you the gradient with respect to W1. You can derive similar expressions for all the other parameters of the network. So yeah, in practice, we're going to use auto-differentiation to do all of this stuff for us, and we don't have to worry about this when we're practically coding neural networks. All we have to do is define the forward function of the model, and auto-differentiation, PyTorch, TensorFlow will be able to evaluate that gradient and help you train that model automatically using autodiff. Okay, so that's the end of this lecture because it's a short lecture today. So just to summarize, the main thing I want you to take away is that neural networks are simply flexible functions that fit to data. The magic of neural networks is that they have universal approximation. They can be trained on many, many different tasks. And we train them using the chain rule and gradient descent. So yeah, thank you very much, and see you next time.